All right, so today we're going to be talking about atmosphere. We've been talking about the planet on a global scale, talking about space. We're going to come just to that first layer of that atmosphere, that bubble that's holding everything in, that's protecting us, that's keeping out all sorts of radiation and debris from space, and is also providing us with habitable temperatures and the oxygen and other gases that we need to survive. So first, the atmosphere is made out of a vast variety of gases, but the four most prevalent gases are nitrogen, oxygen, water vapor, and argon. And you can see that by the time we get to argon, we're already at less than 1%, but it's still the next most available gas. So nitrogen, you can see, is at about 75%. And nitrogen is really helpful in that it basically stops the world from blowing up. Oxygen, you can see, is next at 20%. Now, oxygen is what we breathe, but it is also what allows things to burn. So if we had a higher concentration of oxygen, static electricity, any kind of friction, any spark, and all of the oxygen in the atmosphere would just combust and everything would be over. So that nitrogen is really important for keeping us alive, even though it's not something that our body directly uses. It does keep the oxygen diluted enough that the oxygen itself isn't a danger. Again, we've talked a little bit about the oxygen. Water vapor is another important one. As liquid water evaporates, it turns into water vapor, goes into the air. And depending on where you are geographically, whether you're over, say, a tropical rainforest or a desert, whether it's, what type of season you're in, it can be anywhere from almost 0% in a dry season in a desert on a, hot sunny day to up to 4% when it's really humid over a tropical rainforest. And then we get to argon, which is used in various things, such as, it's a gas in double pane glass and things like that, but really it's just the next most prevalent gas in the atmosphere. So that's what the atmosphere is made of. Let's take a look at what it does and how it's arranged. And we're going to start with that topmost layer, almost in outer space, and that is called the exosphere. Kind of like an exoskeleton, it's going to be on the outside of everything, protecting us. And in that exosphere, particles, molecules, atoms, very, very, very thin, and to the point that they're just, velocity is getting so fast that they're just flying off into space. Not too quickly because, again, just such a low concentration. Also, this is where things like, satellites and space shuttles orbit. Things like that. Below that, so that's in our exosphere. Below that we have the thermosphere. And it is our upper atmosphere. The exosphere is also the upper atmosphere. The gas density is still very, very low. So while temperatures can reach up to 2,000 degrees Celsius, it would still feel very cold because temperature is a measurement of how much energy is in a molecule or a particle. Since there are so few particles, so few molecules, it wouldn't be enough to heat you or make you feel warm because there just isn't enough coming in contact with you. Our picture shows our space shuttle here. It shows Aurora Borealis, and then it's got this jagged line showing that the thermosphere is actually quite a bit bigger. The thermosphere continues for about another 100 miles in between there. They just cut that part out to make the picture smaller. So here now we have the layers in between each of these the transition points in between each of these layers are it's basically the same prefix as the lower level and then pause. So between the thermosphere and the exosphere, we have the thermopause. Between the thermosphere and the mesosphere, we have the mesopause. Now in the mesosphere, we have an increase in particle density that causes temperatures to rise. Down here at the bottom of the thermosphere, we're looking at negative 15 degrees Celsius or so. So while the temperatures are rising, we're still not talking warm. I think we're getting somewhere near maybe 0 degrees Celsius in the mesosphere. But gases are now getting dense enough to slow down and burn up meteors. This is why they have those ceramic tiles on the outside of the space shuttle and everything. Those really start to come into play once you get into the mesosphere. Now here in the stratosphere, we've got the stratopause in between the mesosphere and the stratosphere. In the stratosphere, we have things, like weather balloons, airplanes. Airplanes might actually be in the troposphere. Anyway, the ozone starts in the stratosphere. So now we're starting to get a pretty good concentration of gases. But the ozone happens fairly high up in the stratosphere, and that production causes heat, which increases with height. So it's hot up here, it's colder down here. As we'll talk in a moment, as we've talked before, hot air rises, cold air sinks. So everything in the stratosphere is fairly stagnant. We don't really get any kind of convection currents that we do in the troposphere or that would cause wind. Okay, in the lower atmosphere we have the troposphere, this bottom layer here, and that's where all the weather happens. That's where almost all the water vapor is. Temperatures drop with altitude until we get to that magic spot in the stratosphere where there's that break between the cold and the hot. So down here at ground level, it could be, up to 100 degrees. By the time we get up to the top of the troposphere, anywhere from 0 to 5 degrees. And that happens because the air is getting less and less and less dense. When I was a kid, I lived at 7,000 feet, and then I would go and visit places that were much closer to sea level, and you could just feel the pressure from the air. And this is also an issue with mountain climbers, and there have been all sorts of documented cases of the types of precautions you need to take when you're doing things like climbing Mount Everest, because even though that's still land, it's so high up in the atmosphere that the air is just so has such a low density that it becomes difficult to breathe. So now what happens when all of this stuff starts to move? We get wind. Okay, wind is just moving air. It moves in particular ways and brings lots of, weather and things with it, but it is just moving air. Now basically what happens, from this point on, we're all talking in the troposphere, so down here with the weather. And what is going to happen is that we have all these air particles, and they're down here on the ground, and the ground is warmer than the air around it. So it's going to heat up the particles, and as they heat up, they're going to get less and less dense. Okay, and as they get less dense, they're going to spread out and get higher. Okay, they're gonna get less dense. When things are less dense, that they float, because air is a fluid. It's kind of, it works in physics the same way that water works. So, you think of what floats and sinks in water. It's a similar type of concept of what floats and sinks in the air. That's why helium is, that's why a helium balloon will float up in the air, because the helium is less dense than the atmosphere around it. So as these particles heat up, they get less dense and they rise. And now we have this whole section where there used to be all this air, these air particles, and there's nothing there. So over here have always been these air particles that have been colder. Now the hot air is coming up and pushing them out of place, and so they're going to come down. And look, here's this great spot where the hot air was, and it's going to fill up that spot. And so it's going to be a continual cycle, a current, and we do get convection currents in the ocean as well, but we have this current, and that's what makes wind. The hot air rises, the cold air comes down and sinks and takes its place. This area right here is where you would think of normally as wind happening as that air moves horizontally across the land. Now there are some things that cause air to move differently. Like here is hopefully a picture that you recognize of a weather map. Excuse me. Here we have a high pressure system, so the air is rising. Here we have a low pressure system, the air is going down. We have these circular bars, they're called isobars. The isobars link together places on the earth where the air pressure is the same. So up here in Montana, over here in Nebraska, over here in, I don't know, New Mexico, all those places have the same air pressure. Over here they have the same air pressure. Up here out in the west, out in the Rockies, there's a high pressure. The air is going up, taking with it water vapor and things like that. So we're going to have probably nicer weather. Over here in the plains, we have low pressure. The air is coming down. It's got water in it, and it's going to be trying to move other air out of its way because these pressure systems aren't really all that close to each other. What you would think, the very simplest thing that would happen would be that the air comes down over here in the plains. It comes across, I guess it comes down in the Midwest. It goes across the plains and comes up over the Rockies. But that's not exactly what happens for a few different reasons. A pressure gradient force is a force that tries to equalize pressure differences. So here you can see, I don't know if this is going to show. No, that won't. Let me get a marker that'll show. Over here we've got lines that are fairly close together. And here we've got lines that are far apart. Now the pressure gradient force is going to want just everything to be equal, wants everything to be a nice flat stage, and so that is going to change how the wind moves around. Okay, we can see that in this low pressure system the arrows are showing the way the wind is going, and so they're going counterclockwise in towards the low pressure. Over here in this high pressure system, the lines are going clockwise away from it. So yeah, part of that is the pressure gradient force. Part of that is friction, which is just, two things rubbing against each other, in this case air and the land, the trees, the buildings. That's gonna, it's a lot easier for air to just move across a prairie than to move across a city or move across a mountain. When it gets to a mountain or a building or something, it has to find a different way to go, things like that. But another big factor is the Coriolis force, or the Coriolis effect. And it is a force caused by the rotation of the Earth that causes objects in the northern hemisphere to turn to the right and in the southern hemisphere to turn to the left. Now, that doesn't mean things are actually turning. If you were to look at them from space, the wind would just be going straight across. The problem is that while the wind is going straight across, the Earth is moving underneath it. So while it is a straight movement for the wind, to us on Earth, while we're moving, it ends up feeling very different. And this is, again, another example from some of your readings. So the Earth is like this spinning disc here in number 1. And it's just going, it's spinning. Now somebody decides that they want to make a straight line. So they put a ruler, it's nice and straight, and they draw a line from the center to the outside. The line that is being drawn is straight, but as the disc moves out from underneath it, you get this curve. And so that's basically what the Coriolis effect states, that because the Earth is turning, even though the pressure systems are working and wind is moving in, a continuous direction, because the Earth is turning under it, to us, looking at it from our point of view where we're moving relative to that straight line of wind. We're curving underneath that straight line of wind, so it's not going to feel like a straight line of wind. It's going to feel curved. So next time we'll be talking a little bit more about what happens when all this wind comes, when we get those high pressures and low pressure systems, and what that brings with it. As always, let me know if you have any questions.